Somewhere in the dark, a machine the size of a small car is still moving, and nothing is chasing it, nothing is guiding it. We built it in a single human lifetime, from parts soldered by hands that are now old or gone. 10 trillion years from now, 1,000 times the current age of the universe, that machine may still exist. But here is the vertigo. Almost every landmark we use to say where it is will be gone. The sun burned out, the constellations scattered, the Milky Way itself reshaped beyond recognition, perhaps swallowed into something larger. The object may endure. Its address will not. We can track it tonight to the kilometer, yet we cannot honestly name the galaxy that will hold it. This is that story. If you enjoy stories about the machines we sent to the edge of everything, consider hitting that like and subscribe button. Now, settle in and get yourself comfortable. Let's begin. Picture a specific afternoon, somewhere in the next decade or so, inside a control room in Southern California. An engineer types out a command and sends it toward a spacecraft, the same unremarkable way engineers have done for nearly 50 years. The command climbs onto a radio beam and races outward at the speed of light. It travels for more than 19 hours before it arrives. And this time nothing answers. That is the moment this whole story turns on. Not an explosion, not a collision, not a dramatic failure of any kind, just a silence that begins one day and never lifts. For almost half a century, Voyager 2 has been a conversation, a machine that listens, obeys, and reports back across the dark. On some future date, that conversation will simply end. The spacecraft will not announce it. The spacecraft will not even know it has happened. It will go on doing the single thing it has done without interruption since the summer of 1977, which is move. We tend to imagine the death of a space probe as a kind of ending. It is not. It is a handover. Up to that final signal, Voyager 2 belongs partly to us. We know where it is, what it is doing, how warm it is, how much strength is left in its voice. After that final signal, it belongs entirely to physics. And physics is not sentimental. The laws that will carry the spacecraft forward are the same ones that were carrying it a moment before contact was lost. Nothing about its motion depends on us being able to hear it. This is the first and most important idea in the entire journey, and almost everyone gets it backwards. Losing the spacecraft and stopping the spacecraft are two completely different events, separated by an amount of time so vast that our minds refuse to hold it. So before we follow Voyager 2 into that silence, we have to understand exactly how the silence arrives, because it is already beginning. Let us start with the thing that keeps the spacecraft alive, its power. Voyager 2 does not run on sunlight. Out where it is now, the sun is just another very bright star, far too faint to power anything, so solar panels were never an option. Instead, the spacecraft carries 3 radioisotope thermoelectric generators devices that turn heat directly into electricity. Inside them sits plutonium, slowly decaying, giving off warmth as it does. That warmth becomes the current that runs the computers, the heaters, the radio, and the instruments. It is an elegant, brutal kind of power source. It has no moving parts to wear out. It simply fades, year after year, as reliably as the decay of the atoms inside it. And that is the problem. When Voyager 2 launched, those 3 generators together produced about 470 watts of electrical power, roughly what a few household light bulbs draw. The plutonium inside loses about half of its heat-producing capacity every 87.5 years, but the real day-to-day squeeze is worse than that number suggests, because the thermocouples that convert heat into electricity are degrading too. Add it together, and the spacecraft loses close to 4 watts of usable power every single year. 4 watts does not sound like much, but there is no way to add more. Every watt lost is lost permanently. For decades now, the mission has been a slow, disciplined act of subtraction, a long negotiation with an energy budget that only ever shrinks. For a long time, that negotiation was invisible to the outside world. Engineers turned off heaters no one would miss. They shut down systems that were no longer needed. They kept the science flowing. But eventually the easy sacrifices run out, and you are forced to start switching off the instruments themselves, the very things the spacecraft exists to carry. That threshold has now been crossed, and we are watching it happen in real time. In October of 2024, the mission turned off Voyager 2's plasma science instrument, the device that measured the electrically charged gas flowing around the spacecraft. In March of 2025, they shut down its low-energy charge particle instrument. The cosmic ray subsystem, another of its long-serving detectors, is slated to go dark as the power keeps dropping. Each shutdown is a small, deliberate amputation, performed from 13 billion miles away by people who understand that they are trading pieces of the spacecraft's senses for a little more time. As of early 2026, both Voyager probes are still functioning, still returning data, still stubbornly alive, but the arithmetic is relentless. The engineers believe careful management can keep at least one instrument running into the 2030s. After that, even the instruments will be gone, and the spacecraft will have nothing left to report except the faint fact of its own existence. It is worth pausing on how irreversible each of these shutdowns truly is, because it deepens the sense that the spacecraft is being handed over piece by piece. Consider the cameras. Voyager 2 carried cameras once, the eyes that returned those first close portraits of the outer planets. They were switched off decades ago, not long after the mission's planetary work was done, to conserve power and memory for the instruments that mattered in interstellar space. But they were not merely switched off. The software that operated them was removed from the spacecraft entirely, and on the ground, the specialized computers that once understood that software no longer exist, and the engineers fluent in it have moved on or passed away. Even if someone decided tomorrow that they wanted a final image, there would be no way to command it. The knowledge, the hardware, the code have all quietly dissolved. The cameras are technically still bolted to the spacecraft, pointed out at a sky gone almost entirely dark, and they will never open their eyes again. That is the texture of this long goodbye. It is not one clean shutdown, but a series of small, permanent relinquishments, each one closing a door that cannot be reopened. Long before the final signal, much of what Voyager 2 once was has already been set down and left behind. There is something worth sitting with in that image. A team of people, many of whom were not born when the spacecraft launched, spending their careers deciding gently, precisely which of its senses to switch off next. The mission has become a kind of hospice, not because anyone is giving up, but because the power is finite and honesty demands a plan. Every choice buys weeks or months. None of them can buy forever. Power is not the only clock ticking. Even if the generators held out, a second, quieter countdown runs alongside them, one that has nothing to do with electricity and everything to do with aim. Voyager 2 only reaches us because it points at us. Its dish antenna has to stay locked onto the Earth with remarkable accuracy, or its whisper of a signal sails off into empty space and never arrives. Holding that aim is the job of 16 small thrusters fed from a single tank of a propellant called hydrazine. Every so often, the spacecraft fires a brief puff to nudge itself back into alignment, correcting the slow drift that would otherwise let its antenna wander off Earth. It has been doing this, puff by puff, for decades. At launch, it carried about 100 kilograms of hydrazine, enough, by the mission's own reckoning, to keep the spacecraft oriented into roughly the 2030s. Like the plutonium, the fuel only ever runs down. When it is gone, the thrusters fall silent, the drift goes uncorrected, and the antenna slowly slides off target. The spacecraft could still have power. It could still, in principle, have something to say, but it would be facing the wrong way, speaking into the void, and we would never hear it. There is an even more delicate vulnerability hidden in that system. The hydrazine has to travel from its tank through thin fuel lines to reach the thrusters, and those lines must be kept warm. Out where Voyager 2 drifts, the cold is so profound that without heating, the fuel lines could freeze, and if they froze and cracked, the spacecraft would lose the ability to point at Earth permanently. In an instant, no matter how much fuel or power remained. This is why the endless triage of turning off heaters is so fraught. Every heater switched off to save a watt is a small gamble that some critical line will not freeze. The mission is not only rationing electricity, it is managing temperature, keeping the spacecraft's fragile plumbing just warm enough to keep it aimed at home. So the final silence may not arrive the way we tend to imagine, as a slow dimming of the voice until it fades below hearing. It may arrive suddenly, from any of several directions at once, the last instrument starved of power, the fuel tank run dry, a frozen line snapping in the dark. We do not know which clock will reach zero first. We only know they are all running down together, and that when the first of them stops, the conversation stops with it. And then, eventually, comes the last conversation of all. Voyager 2 speaks to Earth through NASA's Deep Space Network, a set of enormous radio dishes positioned around the planet. Because of the spacecraft's steep path below the plane of the planets, it can only be reached reliably by one particular antenna in the southern hemisphere, a giant dish outside Canberra, in Australia, 70 meters across. A bowl of steel wider than a football field is long, built to catch a whisper from the edge of the solar system. Down that narrow channel flows everything, every command up, every whisper of data back, and whisper barely does it justice. Consider what the signal has become by the time it reaches Earth. It leaves the spacecraft from a transmitter with less broadcasting power than the little bulb inside a refrigerator, a feeble trickle of radio energy flung across more than 13 billion miles of emptiness. Over that immense distance, the signal spreads and thins and weakens according to the pitiless arithmetic of space, until what finally washes over our planet is fainter than almost anything else we deliberately try to detect in the entire sky. It arrives smeared across more than 19 hours of travel time, so faint that the word signal feels too strong for it. It is closer to the memory of a signal, the ghost of one. That we catch it at all is a small miracle of engineering. The task of hearing so frail a transmission falls to that same lone dish outside Canberra, wide enough and sensitive enough to lift it out of the ceaseless noise of the cosmos. A bowl of steel that must be aimed with painstaking precision across the sky and swung to track the spacecraft as the Earth turns beneath it. Everything depends on that one fragile link, a single antenna on the underside of one planet, straining to gather an all but vanished signal out of the dark. It is a thread almost impossibly thin, and threads that thin do not need to be cut to be lost. They need only to fade a fraction below hearing. As the power fades, the radio fades with it. At some point, the spacecraft will no longer have the strength to hold its antenna pointed at Earth, or to push a signal strong enough for even the best dish to catch. Estimates suggest the probes could remain within reach of the Deep Space Network until sometime around the mid-2030s, though every year now carries the quiet caveat that any day could bring the last transmission with no warning at all. There may not be a clean goodbye. More likely, there will be a scheduled contact that produces only noise, and then another, and then a decision made carefully, and probably with some grief to stop listening. That is the moment our part of the story ends. That is the final signal. From that day on, no human being will ever again know precisely where Voyager 2 is. And in that silence, Voyager 2 will not be entirely alone, not in the sense of company, but in the sense of kinship. It will join a tiny, scattered fellowship of machines that humanity has flung past the edge of the solar system, and most of them have already gone quiet. There are 5 human-made objects on escape trajectories out of the solar system, and each one tells the same story of silence. Pioneer 10 and Pioneer 11 went first, launched in the early 1970s as the trailblazers that proved a spacecraft could even survive the passage through the asteroid belt and past Jupiter. Both have long since fallen silent. The last faint contact with Pioneer 10 came in 2003, and with Pioneer 11 years earlier still. They are out there now, powerless, mute, coasting exactly the condition Voyager 2 is approaching. Then came the 2 Voyagers themselves, launched in 1977, still speaking for now but fading. And most recently, New Horizons, the probe that swept past Pluto in 2015 and is still active today, still returning data, but carrying the same kind of dwindling power source and bound, eventually for the same silence. Think about what this fellowship really is. 5 objects, built across 4 decades by a single species on a single planet, each given just enough of a push to leave their star forever, and each destined to spend the overwhelming majority of its existence as a dead, drifting thing that no one is listening to. The active, talking phase of every one of these missions, the years of commands and images and discoveries that fill the history books, is a vanishingly brief prelude. Pioneer 10 and 11 have already crossed from spacecraft into artifacts. The Voyagers are crossing now. New horizons will cross later. Notice one more thing about the silent pioneers, because it quietly previews everything that follows. They stopped talking to us 20 years ago and more, but they did not stop. Wherever Pioneer 10 is right now, at this moment, it is precisely where the laws of motion say it should be, not because we are tracking it, but because nothing out there has reason to move it otherwise. Its silence changed our knowledge of it completely, and changed its motion not at all. That is the exact lesson Voyager 2 is about to teach on a far grander scale, and the pioneers are already demonstrating it in miniature. A silent machine is not a stopped machine. It is simply a machine we can no longer hear, still faithfully obeying the only law that ever really governed it. Here is where almost everyone's intuition fails. It feels, emotionally, as though that silence should be the end. The spacecraft goes quiet, and so, in our imagination, it stops a dead thing hanging in the dark, but nothing could be further from what actually happens. The moment communication ends is not the moment the journey ends. It is the moment the journey stops being observed. The spacecraft does not slow down. It does not drift to a halt. It does not need our commands, our power, or our attention to keep moving, because in the near-perfect emptiness of interstellar space, there is almost nothing to stop it. This is Isaac Newton's oldest and simplest law, playing out on the largest imaginable stage. An object in motion stays in motion unless something pushes on it. On Earth, things always stop because something always pushes back friction, air, the ground. But between the stars there is no road to grind against and no meaningful air to resist. The space Voyager 2 travels through is not a perfect vacuum. It holds a thin haze of atoms, a scattering of dust, faint magnetic fields, and the pressure of starlight. Those things exist, and over enormous spans of time they matter, and we will come to them. But they are so tenuous that over any human timescale their braking effect is essentially nothing. The spacecraft coasts. It has been coasting, engines silent, for decades already. The end of communication changes only one thing: whether anyone back home can watch it coast. So let us look, one last time, while we still can, at exactly what we are handing over to physics. This is the part we know with real confidence, not a projection, not a model, but a measurement. As of the start of 2026, Voyager 2 is roughly 143 astronomical units from Earth. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So the spacecraft sits more than 13 billion miles away, so distant that its radio signal, moving at the fastest speed the universe allows, needs the better part of a day just to reach us. It is moving away from the Sun at about 15 kilometers every second. That is roughly 34,000 miles per hour, or a little more than 3 astronomical units of distance gained each year. And it is not travelling outward along the tidy flat plane where the planets orbit. It is plunging downward and away, angled steeply around 48 degrees below that plane aimed toward the southern constellations Sagittarius and Pavo. Voyager 1 went high and north. Voyager 2 went low and south. They are drifting apart into opposite corners of the sky, 2 lonely objects headed in almost opposite directions, and they will never be near each other again. Those numbers, the position, the speed, the direction are the inheritance. Whatever happens to Voyager 2 across the unthinkable future, it begins from precisely this measured starting line. And for the first stretch beyond the last signal, that starting line lets us predict the journey with surprising confidence. This is the best known portion of everything that is to come, and it is worth walking through carefully, because it is also the last stretch that will behave itself. But to understand where the spacecraft goes next, we have to clear up a confusion that trips up nearly everyone, the meaning of the phrase, leaving the solar system. Because Voyager 2 has already, in one specific and famous sense, left it, and in another, far larger sense, it has barely begun to. Back in late 2018, Voyager 2 crossed a boundary called the heliopause. To picture what that is, you have to understand that the Sun does more than shine. It blows a constant, supersonic wind of charged particles streaming out in every direction, carving out an enormous bubble in the surrounding galaxy. That bubble is the heliosphere, and the spacecraft spent its whole life inside it, immersed in the sun's own wind. The heliopause is the bubble's outer skin, the place where the sun's wind finally loses its push and gives way to the gas of interstellar space. Voyager 2 had crossed an inner boundary years earlier, the termination shock at about 84 astronomical units, where the solar wind first slows and piles up, and then, in 2018, at around 119 astronomical units, it pushed through the heliopause itself and began for the first time to directly sample the material that lies between the stars. That was the confirmed, measured event that let NASA say the spacecraft had entered interstellar space. And that is true, but it is also easy to misread. Crossing into interstellar space is not the same as escaping the sun's grip. The heliopause is where the sun's wind ends. It is emphatically not where the sun's gravity ends. Those two frontiers are separated by a gulf so wide, it makes the first one look like a doorstep. The sun's gravitational reach its actual gravitational domain. The region where its pull still dominates over the pull of other stars extends outward perhaps 2 light-years, and filling much of that vast, dark, still-bound territory is a structure we have never seen directly but are confident exists: the Oort Cloud. The Oort Cloud is the sun's true outer wilderness. It is a colossal, roughly spherical swarm of icy bodies, the deep frozen leftovers of the solar system's birth, thought to begin thousands of astronomical units out and stretch outward to somewhere in the neighbourhood of 100,000 astronomical units, a substantial fraction of the way to the nearest star. This is the reservoir that occasionally sends long-period comets falling inward toward the inner planets on journeys lasting thousands of years. Scientific consensus treats this cloud, not the heliopause, as the meaningful gravitational edge of the solar system, the place beyond which the pull of other stars finally begins to win, and Voyager 2 has not remotely crossed it. It has only just left the sun's wind. It has not left the sun's family of objects at all. The numbers here are genuinely staggering, and they reset the whole clock of the story. At its current speed, Voyager 2 will take something like 300 years merely to reach the inner fringes of the Oort Cloud, to pass all the way through it, to finally coast beyond the outermost icy bodies still faintly bound to our sun, will take on the order of 30,000 years. 30,000 years. Ponder what that means. Every command we ever sent, every image it ever returned, every human being who has ever worked on the mission or ever will, all of that happens in the first eye blink of a crossing that will still be underway 300 centuries after the last engineer stops listening. The spacecraft will spend longer silently traversing the sun's own backyard than our species has spent building cities. And through that entire immense passage, one thing stays reassuringly predictable. Within the sun's gravitational domain, the sun is still the boss. The spacecraft is climbing outward on what astronomers call a hyperbolic escape trajectory, a path with just enough speed to break free forever, curving gently as the sun's fading pull bends it, but never turning back. It is a little like a stone thrown hard enough to leave a planet entirely. It slows as it climbs, its path bends, but it never falls home. For these first tens of thousands of years, if you wanted to know where Voyager 2 would be, you would mostly need to account for one dominant gravitational influence, our own sun, plus a handful of small, well-understood tugs. That is a solvable problem. That is why this leg of the journey is the one we can still chart with real precision, even though no one will be alive to confirm it. The physics is clean, the variables are few, the answer holds. But that clean simplicity is a temporary gift, and it is running out even as the spacecraft climbs. Because as Voyager 2 nears the outer reaches of the Oort Cloud, tens of thousands of years from now, the sun's authority weakens toward nothing, and the gravity of other stars begins, for the first time, to matter more than the gravity of home. The moment that balance tips, the spacecraft stops being an object leaving the sun and becomes an object adrift among the stars, subject to a crowd of gravitational voices instead of one. And the calculation that was so clean begins, slowly at first, to come apart. There is one more thing to hold on to before we follow it out there, and it is a distinction that will matter enormously later. All of this, the fading power, the dying instruments, the last signal, the silent coast through the Oort Cloud describes a spacecraft that is still, in every meaningful physical sense, itself. Its structure is intact. Its trajectory is a smooth, calculable curve. It is a machine that has gone quiet, not an object that has been transformed. That distinction between a thing that continues, a thing that stays intact, and a thing that remains recognizable is going to become the hidden spine of this entire story. For now, near the beginning of the silence, Voyager 2 is all three at once. It continues. It is intact. It is recognizably the spacecraft we built. Hold that image, because each larger span of time we cross from here will quietly strip one of those three away. We are, at this stage, still standing on solid ground. Everything described so far rests either on direct measurement or on physics so well understood that the predictions are about as trustworthy as anything in science can be. We know the spacecraft's speed and heading because we measured them. We know it will coast because there is nothing out there to stop it. We know roughly how long the Oort Cloud crossing takes because the distances and the velocity are both nailed down. This is the deterministic heart of the journey, the part where the universe still behaves like clockwork and the answers hold. But at the very edge of that clockwork sits the first hint of everything that is coming. Somewhere around 40,000 years from now, while Voyager 2 is still finishing its long exit from the Oort Cloud, its silent path will carry it into the vicinity of another star for the very first time. A small, dim red dwarf in the direction of the constellation Andromeda, catalogued as Ross 248. It is the first named encounter in the spacecraft's future, the first time since leaving the Sun that another star will come close enough to matter, and almost everything about how people describe that encounter is wrong. They speak of Voyager 2 reaching Ross 248, of the probe being aimed at it, of an arrival as though the spacecraft were a traveller with a destination in mind. It is none of those things, and untangling what that encounter really is a near miss. Measured across a gulf still enormously wide, between two objects that are both moving, neither aware of the other, is where the certainty starts to dissolve, and where the real story of this journey begins. Around 40,000 years from now, a small red star and a silent machine will drift past each other in the dark, and neither will register the event in any way. There will be no flash, no signal, no moment of contact. If you could somehow be standing on the spacecraft at that instant, you would not even be sure which of the thousands of faint points around you was the one the encounter is named for. And yet this quiet non-event is the first real appointment in Voyager 2's future. The first time since it left the Sun's neighbourhood that another star will come close enough to be worth naming. The star is Ross 248, a dim red dwarf currently sitting about 10 light-years away in the direction of the constellation Andromeda, far too faint to see with the unaided eye. And the very first thing to understand about this encounter is that Voyager 2 is not travelling toward it. That sounds like a contradiction. How can the spacecraft pass a star it is not heading for? The answer dissolves one of the most common misconceptions about this whole journey, and it is this. The star is moving too. Ross 248 is not a fixed lamp hanging in space, waiting patiently for a probe to arrive. It is itself hurtling through the galaxy, on its own path, at its own speed, and that path happens to be carrying it toward our corner of the Milky Way right now. Every star you have ever seen is in motion, orbiting the distant centre of the galaxy, drifting relative to its neighbours. The night sky looks frozen only because those motions are so slow against such vast distances that a single human lifetime cannot register them. But stretch the clock to tens of thousands of years and the sky rearranges itself completely. The constellations we know will smear and dissolve, and Ross 248 in particular is on the move in a way that matters enormously here, because this little star is approaching. Over the next 30-some thousand years, Ross 248 will slide closer and closer to our Sun, and at its nearest around 36,000 years from now, it will briefly become the closest star to our solar system of all, edging out even the Alpha Centauri system, coming to within roughly 3 light-years of the Sun and holding that title for something like 9,000 years before it recedes again. So when we say Voyager 2 will pass Ross 248, a large part of what is actually happening is that the star is coming to meet the region of space. The spacecraft is drifting through. The encounter is a coincidence of two independent travelers arriving in the same neighborhood at roughly the same time. One, a natural star sweeping through on its galactic orbit. The other, a piece of 1970s engineering coasting outward on momentum alone. Picture two strangers crossing an enormous, echoing plaza from different entrances, each following their own errand, whose routes happen to bring them within shouting distance near the center for a few seconds before they continue on and never meet again. That is the encounter. Not a rendezvous, a crossing. To see why astronomers can predict this crossing at all, and why their confidence has limits, you have to understand what actually goes into the calculation. To describe the future path of any object coasting freely through space, you need exactly 6 numbers. 3 of them fix where it is at a given moment, its position in 3 dimensions. The other 3 fix how it is moving its velocity in 3 dimensions. Feed those 6 numbers into the laws of motion, add the gravitational pulls acting on it, and you can project the object forward in time. For Voyager 2, we have all 6 numbers to extraordinary precision because we measured them ourselves. We tracked the spacecraft for half a century. We know its position and its velocity better than we know almost anything else in the outer solar system. The harder half of the problem is the star. To predict where Ross 248 will be in 40,000 years, you need its 6 numbers too, and a star does not report them to you. You have to extract each one from its faint light. Its distance comes from parallax, the tiny apparent shift in the star's position as the Earth swings around the Sun across the year. The smaller the shift, the farther the star. Its sideways drift across the sky, its proper motion is measured by comparing precise images taken years apart, and its motion straight toward us or away from us comes from the spectrum of its light, from the subtle stretching or compression of its color as it recedes or approaches. Assemble those pieces and you have the star's full state, where it is and where it is going. Do the same for the spacecraft. Then run both forward together and find the moment when the gap between them is smallest. That moment of closest approach is the encounter. For Ross 248, the answer that falls out is a passage of about 1 7/10 light years, roughly 40,000 years from now. Now hold that distance up to the light, because this is where the story quietly resets your sense of scale. 1 7/10 light years. In astronomical shorthand, that is a little over half a parsec being about 3¼ light years, one of the standard yardsticks astronomers use for the gaps between stars. Half a parsec sounds intimate when you say it quickly. It is not. It is a gulf so wide that calling it a close approach is only meaningful against the even more staggering emptiness that surrounds it. 1 7/10 light years is just under 10 trillion miles. It is over 100,000 times the distance from the Earth to the Sun. Consider how far Voyager 2 has managed to travel in nearly 50 years of relentless flight. About 13 billion miles, which is not yet even 1/400th of a single light year. At that same pace, crossing 1 7/10 light years of open space would itself take tens of thousands of years. That is the closeness of this encounter. The spacecraft and the star will be within 1 7/10 light years of each other, which means the spacecraft will remain further from that star than it would need to travel across dozens of human civilizations worth of time to reach it. So let us be precise about what this encounter is and is not, because the language matters, and sloppy language has done real damage to how people imagine Voyager's future. There are 4 completely different things that could happen when a spacecraft and a star come near one another, and they are separated by unimaginable gaps in scale. The first is a distant passage coming within some large astronomical distance, close in the way that 2 cities on opposite sides of a continent are close compared to 2 cities on different planets. The second is entering the star's planetary system, actually crossing in among whatever worlds orbit it, a region measured in a few light hours, not light years. The third is gravitational capture, passing so close and so slow that the star's gravity seizes the spacecraft and bends it into orbit. And the fourth is a physical collision, an almost absurdly improbable direct hit on the star or one of its planets. What happens at Ross 248 is emphatically, overwhelmingly the first of these and nothing more. At 1 7/10 light years, the star exerts essentially no meaningful pull on the spacecraft. Voyager 2 will not enter its planetary system. It will not be captured. It will not collide. From the spacecraft's silent vantage, Ross 248 will simply brighten for a few thousand years into a slightly less dim point of light among countless others, reach its nearest, and then fade again as the two travelers continue on their separate ways. To say the probe reaches that star, or arrives at it, is to compress 10 trillion miles of emptiness into a word it cannot bear. And this is the deeper reason the encounter is not a destination. Nothing aimed the spacecraft there. Voyager 2's direction was not chosen to intercept Ross 248 or any other star. Its heading is a leftover, the accumulated result of where the planets happened to fling it during its grand tour of the outer solar system. Decades ago, it flew where the gravity of Jupiter and Saturn and Neptune sent it, and it has been coasting along that inherited line ever since. The alignment with Ross 248 is pure coincidence, a matter of the star wandering into the right region of sky at roughly the right time. The spacecraft is not a traveller with an itinerary. It is a thrown object, and the star is a moving target that no one was aiming at. When the two happen to draw near, it is not the fulfillment of a plan. It is a chance intersection of two trajectories that were never coordinated and never will be. Voyager 2's twin makes the same point from a different direction. Voyager 1, which left the solar system on a wholly different heading, climbing high above the plane of the planets instead of plunging below. It has its own lonely appointment with a star, and it is a completely different star. In roughly 40,000 years, Voyager 1 is projected to pass within about 1.5 light-years of a faint red dwarf catalogued as Gliese 445, a star drifting in from the direction of the constellation Camelopardalis. Two spacecraft, launched 2 weeks apart, from the same planet, by the same people, and their nearest stellar encounters are with two entirely unrelated stars, in two different regions of the sky, reached by two paths no one designed. Nothing about either encounter was chosen. Each probe simply inherited a direction from the gravitational shove of the planets it visited, and each is now coasting along that inherited line toward whatever star happens to wander near it. The pattern is the message. These are not journeys with destinations. They are trajectories with coincidences. After Ross 248, the appointments grow sparser and stranger. The next named encounter in Voyager 2's future is with Sirius, the brightest star in Earth's night sky. A brilliant blue-white beacon currently about 8.5 light-years away. Something like 296,000 years from now, the spacecraft's path will bring it within roughly 4.5 light-years of Sirius. Sit with those numbers for a moment. That is nearly 300,000 years into the future, a span longer than our species has existed, and the encounter is a passage more than twice as distant as the one with Ross 248. If 1 7/10 light-years barely qualifies as a meeting, 4.5 light-years is scarcely even a wave across a crowded room. By the standards of the galaxy, this is still a notable approach, because the galaxy is so empty that even coming within a few light-years of a star is comparatively rare. But it underlines the pattern. These are not stops on a route. They are the handful of moments, scattered across hundreds of thousands of years, when the vast solitude of interstellar space is interrupted by another star passing at a merely enormous distance rather than an unimaginable one. Here we have to confront something uncomfortable about even these carefully computed encounters. The list is not fixed, it is a draft, and it keeps being rewritten. Everything we can say about which stars Voyager 2 will pass, and when, and how closely, depends entirely on how well we know the 6 numbers of every nearby star. And our knowledge of those numbers has been transformed, recently and dramatically, by a single instrument. That instrument is Gaia, a European space observatory whose entire purpose was to measure the positions, distances and motions of more than 1 billion stars, with a precision no earlier survey came close to matching. Before Gaia, our map of the local stellar neighbourhood was good but coarse. The projected encounters of the Voyager and Pioneer spacecraft were educated estimates built on shakier stellar data. When Gaia's measurements arrived, astronomers were able to redo those projections with far sharper inputs, better distances, better proper motions, better velocities, and the encounter lists were revised accordingly. It was Gaia's precise catalogue that let researchers pin down these passages, tracing the Voyager's inherited trajectories forward and matching them against the accurately mapped paths of the stars they might approach. The Ross 248 encounter, the Sirius encounter, the confident statements about closest approach distances, these rest on Gaia's map of where the stars are and where they are going. But a map is only as final as the survey behind it, and surveys improve. Each new release of Gaia data refines the numbers again. Future observatories will refine them further still, and every refinement can shuffle the itinerary, nudge an encounter closer or farther, earlier or later, or reveal an approach nobody had flagged before. Think of it less like a fixed schedule and more like a long-range weather forecast. For the near term, the prediction is trustworthy, the physics is clean and the inputs are solid, but push the forecast far enough out, and small uncertainties in the starting data compound into large uncertainties in the result. A tiny error in a distant star's measured velocity, harmless over 1,000 years, can grow into a wildly different predicted position over 100,000. The encounter list is a snapshot of our current best knowledge, accurate, useful, and provisional. It tells you what the sky looks like it will do, given what we can measure today. It does not promise what the sky will actually do. You can watch this provisionality directly in the numbers themselves. Different analyses, using different data and different assumptions, do not perfectly agree even on the flagship Ross 248 encounter. NASA's figures put the closest approach at about 1 7/10 light years. Other careful calculations have placed it closer to 6/10 of a parsec, which is nearly 2 light years. The gap between those answers, a few tenths of a light year, may sound like a quibble, but it is a revealing one. It means that even our single best-known future stellar encounter, the one we cite most confidently, has a built-in wobble of trillions of miles depending on whose calculation you trust. If the flagship prediction carries that much slack 40,000 years out, imagine how little the numbers can be trusted 40 million years out, or 40 billion. The wobble does not shrink with time, it grows, and there is a further, quieter problem lurking underneath even that. Gaia mapped 1 billion stars, which sounds like everything, but it is not. There are stars too dim, too distant, or too obscured to have been catalogued at all, especially the smallest and faintest red dwarfs, which are the most common stars in the galaxy and the hardest to see. Any one of them could, in principle, drift across Voyager 2's path, far more closely than any star we currently know about, and we would have no way to have predicted it, because the star simply is not on our map yet. The encounters we can name are the encounters with stars we happen to have measured. The universe is under no obligation to send only catalogued stars near the spacecraft. Our list of future approaches is not a list of everything that will happen. It is a list of everything we can currently see coming. And stars are not the only things adrift out there that we cannot see coming. In recent years, astronomers have grown increasingly convinced that interstellar space is populated by a vast, hidden population of rogue planets, starless worlds, flung out of the star systems where they formed and now wandering the galaxy alone, dark and cold, and effectively invisible. There may be billions of them, perhaps even more rogue planets than there are stars, drifting between the star systems in the blackness where nothing illuminates them. We cannot map them. We cannot catalogue them. A rogue planet emits almost no light of its own, and unless one happens to pass in front of a distant star at exactly the right moment for us to notice, it leaves no trace we can detect from here. They are, for the purposes of prediction, a completely dark variable, and any one of them could quietly rewrite Voyager 2's path. A rogue planet does not need to strike the spacecraft to matter. It only needs to pass near enough for its gravity to tug. One of the researchers who studied the Voyager's long-term future put it plainly: a mildly close encounter with a wandering planet could change the itinerary of the spacecraft, nudging it onto a slightly different course that then compounds over the ages into a wholly different path. And because these worlds are invisible to us, such an encounter is not something we could ever predict. It would simply happen, out in the dark, unseen and unrecorded. This is the difference between a list that is merely unfinished and a list that can never be finished. An incomplete star catalogue can, in principle, be completed. Point a good enough telescope at the sky for long enough, and you will eventually find the stars you missed. But you cannot catalogue what emits no light: the rogue planets, The faintest dwarfs, the dark drifting mass of the galaxy, these guarantee that our forecast of Voyager 2's encounters is not just currently incomplete, but permanently open, forever missing an unknown number of terms we have no way to fill in. Every honest projection carries this silent asterisk. It describes what the visible galaxy will do, and says nothing about the invisible one moving right alongside it. Now stand back and look at the shape of what we have. Ross 248 at around 40,000 years, Sirius at around 296,000 years, a scattering of other modelled approaches over the following few million years. Careful analysis using the Gaia data has established that, across the next 5, destined for a remarkably lonely passage through an extraordinarily empty stretch of the galaxy. 5 million years of computed solitude. That is an astonishing achievement of prediction, and it should be honoured as one. But now recall the question this whole journey is meant to answer. Where will Voyager 2 be in 10 trillion years? Set 5 million against 10 trillion, and the ground opens beneath you. 10 trillion is 2 million times larger than 5 million. Everything we have just spent all this time charting every named star, every computed passage, the entire hard-won catalogue of the spacecraft's future, fits inside the first 2/millionth of the timescale we are actually asking about. If you compress the full 10 trillion year journey into a single year, then all of these carefully calculated stellar encounters, from Ross 248 to the last modelled approach 5 million years out, would all be over within the first 16 seconds of the first day of January. Everything astronomy can currently say about which stars Voyager 2 will pass amounts to a bright, sharp, confident sliver at the very beginning of a reel that runs, in this analogy, for a full year. The rest of that reel, the overwhelming, near-total remainder, is dark. Not because nothing happens in it, because it is unknowable by the methods that gave us the sliver. This is the crucial pivot of the entire story, so let us be exact about why the calculation runs out rather than simply getting harder. It is not that astronomers lack the computing power to project further. It is that the very method breaks down. Star-by-star encounter prediction works beautifully as long as two conditions hold. You can identify the relevant stars, and their motions stay predictable across the span you are projecting. Over thousands and even a few million years, both conditions roughly hold. The nearby stars are catalogued, their paths are steady enough, and the spacecraft's inherited trajectory is a clean line, bending only gently under the diffuse pull of the whole galaxy. But push past a few million years and both conditions collapse. Uncatalogued stars accumulate into the reckoning. The measured stars drift far enough that today's small uncertainties bloom into total ignorance of their positions, and the stars themselves do not hold still relative to one another the way the neat calculation assumes they weave and scatter, their gravity nudging each other and everything between them onto new paths. Beyond a certain horizon, asking which specific star will Voyager 2 pass next stops being a question with a computable answer. There are simply too many movers, too poorly known, too far ahead. Notice, too, what has quietly happened to the character of our predictions over the course of this journey. Early in the journey, we could speak in the language of certainty, measured position, measured velocity, a clean escape from the sun, a coast through the Oort Cloud governed by one dominant gravitational voice. Here, in the era of stellar encounters, we have slipped into a softer language without quite noticing. We say Voyager 2 will, probably, pass Ross 248 at about 1 7/10 light years, as far as we can currently tell. We hedge, because the inputs are provisional and the timescales are long. That shift in language is not carelessness. It is honesty tracking reality. The universe is becoming less predictable to us the further out we look, and the words are simply admitting it. At first, this journey dealt in measurement. Now, it deals in calculation. And calculation, however sophisticated, is only ever as trustworthy as the map it is built on and the timescale it is stretched across. And we have just watched both of those give way. So where does that leave the spacecraft? And us? It leaves Voyager 2 on a trajectory we can chart in detail for the first stretch, sketch with fading confidence across the first few million years, and then nothing. A blank. And it leaves us needing an entirely different way of thinking, because the star-by-star approach that carried us this far has reached its natural end. If we cannot follow the spacecraft from one specific star to the next across 10 trillion years, then the only honest path forward is to stop tracking individual encounters altogether and ask a larger question. Not which star will it pass, but what is the spacecraft doing inside the galaxy as a whole? Because here is the thing that the neat straight line of the trajectory calculation has been hiding from us all along. Voyager 2 is not really flying in a straight line at all. It never was. That clean escape path, that gentle hyperbolic curve away from the sun, is a local illusion true enough over thousands of years and a few light years, but false over millions of years and thousands of light years. On the largest scale, the spacecraft is not leaving the galaxy. It is not even trying to. It is falling into a vast, slow, sweeping orbit around the distant heart of the Milky Way, exactly as our sun does, exactly as every star around us does bound to the galaxy, carried along in its immense rotation, one more tiny object, riding the same current as 400 billion stars. The gentle curve we so carefully computed is just the first, almost imperceptible arc of a turn that takes hundreds of millions of years to complete. And once you understand that Voyager 2 is on a galactic orbit rather than a straight escape, the entire question of its future changes shape. The spacecraft is no longer an arrow shot into the dark. It is a passenger on a wheel so enormous that a single revolution outlasts the rise and fall of mountain ranges, a wheel that will turn and turn again, tens of thousands of times before 10 trillion years have elapsed. It is time to stop watching the stars slide past the spacecraft and start watching the galaxy itself take hold of it. Forget the spacecraft for a moment and think about a leaf on a river. If you watch it for a few seconds, it seems to travel in a straight line, sliding smoothly across the surface. You could measure its speed, note its direction, and confidently predict where it will be a moment later. But that straight line is a lie of scale. The leaf is not really going straight at all. It is being carried by a current that curves with the riverbed, and if you followed it for a mile, you would watch it bend around every meander, drawn along by a flow far larger than itself. Its true motion is not the little straight dash you measured. Its true motion is the shape of the whole river. Voyager 2 is that leaf, and the Milky Way is that river. Everything we charted a moment ago, the clean escape from the sun, the gentle hyperbolic curve, the careful line drawn past Ross, 248, is the little straight dash. It is accurate over thousands of years and a few light years, and it is completely misleading about what happens over millions of years and thousands of light years, because the spacecraft is not escaping the galaxy. It cannot escape the galaxy. It is moving nowhere near fast enough. The same 15 kilometers per second that lets it break free of the sun forever is a crawl compared to what would be needed to climb out of the Milky Way's enormous gravitational well. And so, just like the sun, just like every star you have ever seen, Voyager 2 is bound. It has joined the great slow wheel of the galaxy, and from here on, the galaxy is in charge. This is the reframing everything has been building toward. At the start, the dominant gravitational voice was the sun. Then it was a handful of passing stars. Now, it is the entire Milky Way, 400 billion stars, and a vast invisible mass of dark matter, all pulling together, their combined gravity bending the spacecraft into a path that answers to the galaxy as a whole rather than to any single object within it. The spacecraft has become a citizen of the galaxy, subject to its rotation, orbiting its distant center along with everything else. And that orbit is almost incomprehensibly grand. Our sun, and the whole neighborhood of stars around it, circles the center of the Milky Way roughly once every 225 to 250 million years. That single figure reshapes the entire question. That Voyager 2, drifting along with the local stars, is on just such an orbit it will complete one loop around the galactic center about every 225 million years, and it will keep doing so, lap after lap, for as long as it remains bound. The last time our sun was at this same point in its galactic orbit, the first dinosaurs were only just appearing on Earth. One turn of this wheel spans roughly the entire stretch, from those first dinosaurs to today. And the question we are chasing 10 trillion years is not one turn, Divide 10 trillion by 225 million, and you get a number in the tens of thousands. Voyager 2, if it survives and stays bound, will circle the heart of the galaxy something like 40,000 times before our timescale is up. 40,000 laps of a track so vast that a single lap dwarfs the history of animals, so the straight line is gone. In its place is a wheel, and not even a clean repeating wheel, because a galactic orbit is nothing like the tidy, near-perfect ellipse of a planet circling a star. A planet orbits a single dominant mass concentrated in one point, and so it traces the same smooth path again and again. But the Milky Way's mass is not in one point. It is smeared across 100,000 light-years stars, gas, dark matter, spiral arms, a sprawling, lumpy, ever-shifting distribution. An orbit through that is a looping, weaving, precessing thing that never quite repeats, drifting a little each time around, its exact shape depending on the ever-changing arrangement of everything else in the galaxy. Voyager 2's path is not a groove. It will retrace 40,000 times. It is 40,000 slightly different loops, each one nudged by the galaxy's changing gravity into something a little unlike the last. And that constant nudging is where the real dismantling of predictability begins. Because as the spacecraft sweeps around the galaxy on its long orbit, it does not travel through empty space. It passes stars. Over hundreds of millions of years, over billions of years, over the immense spans we are now dealing with, Voyager 2 will drift near countless stars, most of them at the same staggering distances we met before. A light year or more, close enough to notice but far too distant to matter much individually. Yet gravity never fully switches off. Every one of those passing stars gives the spacecraft the faintest gravitational tug, a whisper of a pull, redirecting its path by an amount too small to measure in any single encounter. And here is the crucial thing. Those tiny tugs accumulate. 1 is nothing. 1,000 is nothing much. But over billions of years and millions of encounters, they add up into a slow, relentless randomization of the spacecraft's orbit. This process even has a name among astronomers who study the motions of stars: gravitational scattering. It is the reason the neat orbit is only ever approximate. Each distant stellar passage deals the spacecraft's trajectory, a tiny random shove, and the sum of all those shoves, across cosmic time, is a path that wanders further and further from anything we could have predicted at the start. This is the mechanism that finally severs the link between the measured present and the deep future. Once, we could predict the spacecraft's path because one gravitational voice dominated, and the variables were few. Then the calculation frayed because the stars were too many and too poorly mapped. Now we can see why the fraying is not a temporary limitation but a permanent one. It is not that we lack the data to compute the effect of the next stellar encounter. It is that the encounters are effectively random, and random shoves compound. A system driven by the cumulative effect of countless tiny, unpredictable nudges is not something you can extrapolate through. It is the gravitational equivalent of trying to predict exactly where a single molecule of cream will end up after you stir it into coffee. You know the physics of every collision perfectly. You still cannot say where the molecule goes, because the answer depends on a chain of interactions too long and too sensitive to follow. Voyager 2's orbit, across billions of years, becomes exactly that kind of problem. The trajectory does not stop existing. It stops being knowable. So what can gravitational scattering actually do to the spacecraft across enough time? There is a spectrum of outcomes, and it is worth walking through them carefully, because this is where a lot of loose talk goes wrong. At the mild end, the most common effect is simply what we have described: a gradual reshaping of the orbit, the spacecraft drifting onto a somewhat different loop around the galaxy, then another, and another, its path slowly wandering through the range of orbits available to objects in its region. This is the overwhelmingly likely story for most of the timescale. Not a dramatic event, but a patient, cumulative rearranging. Further along the spectrum, a closer or better timed stellar passage could give the spacecraft a larger kick, flinging it onto a substantially different orbit, perhaps one that carries it much closer to the crowded galactic center on some laps, or much farther out into the sparse galactic suburbs on others. And at the extreme rare end of the spectrum, the accumulated kicks, or one unusually strong one, could in principle add enough energy to the spacecraft's motion to unbind it from the galaxy altogether, scattering it outward until it drifts free into intergalactic space. We will come back to that possibility because it matters enormously later on. But the key point for now is that these are possibilities arranged by likelihood, not a single fixed fate. Gentle reshaping is common. A large orbital change is possible. Ejection is rare and slow to arrive. The spacecraft's future is not one path, but a widening fan of paths, and gravitational scattering is what spreads that fan wider with every passing eon. But now we have to guard against a misconception that the word encounter tends to plant, because it is exactly the kind of false drama the whole story is meant to avoid. When we say Voyager 2 will pass countless stars and be scattered by them, it is tempting to imagine near collisions, the spacecraft threading between blazing suns, dodging catastrophe. Nothing could be further from the truth. The defining fact of the galaxy is not how crowded it is how empty it is. We met this emptiness earlier, at the scale of individual encounters, and it only deepens here. The stars of the Milky Way are so widely separated that an actual physical collision between the spacecraft and a star is almost unimaginably unlikely. The researchers who studied the Voyager's long-term fate estimated that the timescale for one of these spacecraft to actually strike a star is on the order of 10 to the 20th power years. A 1 followed by 20 zeros. That is 100 quintillion years. Set that against our question of 10 trillion years, 10 to the 13th, and the collision timescale is roughly 10 million times longer than the entire span we are asking about. In other words, across the whole 10 trillion years of this journey, the odds that Voyager 2 ever physically hits a star remain vanishingly small. The scattering that reshapes its orbit is caused not by near misses but by distant, gentle passages stars a light year or more away, tugging softly, never remotely close to contact. The galaxy rearranges the spacecraft's path not by threatening it, but by brushing against it, over and over, from far away, for billions of years. There is a second way the galaxy reaches out and reshapes the spacecraft's path, and it has nothing to do with stars at all. Scattered through the Milky Way are enormous clouds of gas and dust, vast, cold, diffuse structures, some of them light years across, containing enough material to birth thousands of stars. Voyager 2 will drift through these clouds on its long orbits, and here the spacecraft's particular trajectory makes things more interesting. Its path around the galaxy is not confined to the flat plane where most of the galaxy's material lies. It rises above that plane and sinks below it, oscillating up and down as it circles, and it is precisely above and below the plane, on those excursions, that the spacecraft spends its time in the regions where certain clouds are thickest. Most of the time, drifting through such a cloud does little but very gently erode the spacecraft's surface, a matter we will return to. But a cloud is not just an abrasive haze, it is a concentration of mass, and mass means gravity. The researchers who modelled the Voyager's deep future noted that these clouds carry so much material gathered in one region that they can actually bend the trajectory of a passing spacecraft, tugging it off its previous course and flinging it onto a new orbit, sometimes casting it farther out toward the galaxy's edge, sometimes deflecting it deeper toward the core. A single massive cloud, encountered at the right angle, can do in one passage what thousands of distant stellar tugs do over eons. Hand the spacecraft a decisive shove onto a path it was not previously on. And like everything else at this scale, exactly when and where such an encounter happens is not something any present calculation can foresee. It is one more source of redirection, one more randomizing hand, waiting in the dark along a route we cannot chart. That distinction between an orbit being reshaped and an object being destroyed is going to matter more and more as we go. For now, hold on to this. Across 10 trillion years, Voyager 2 is far, far more likely to be gently redirected 1,000 times than to be struck even once. The threat to its predictability is not violence, it is accumulation. And here is the next layer of the collapse, the one that turns a difficult problem into an impossible one. So far we have been talking as though the galaxy itself stays put, as though Voyager 2 orbits within a fixed Milky Way, whose gravity we could at least describe, even if we cannot track every star. But the galaxy does not stay put. Over the spans we are now considering, the Milky Way is not a stable backdrop. It is a body in motion, changing, evolving, and on a possible collision course with a giant. That giant is the Andromeda Galaxy, our nearest large neighbour, a vast spiral currently about 2.5 million light-years away and drifting toward us. For decades, the story told about Andromeda was one of grim certainty. The two galaxies were destined to collide in roughly 4 to 5 billion years, merging in a slow gravitational cataclysm into a single elliptical galaxy that some astronomers nicknamed Milky Way. That merger was treated as a fixed event on the calendar of the future, as reliable as the sun's own aging. And if it were fixed, it would tell us a great deal about the environment Voyager 2 will inhabit, because whatever galaxy the spacecraft is bound to, it rides along through whatever happens to that galaxy. But that certainty has recently cracked, and the crack is instructive. In 2025, a team of astronomers led by Til Sawala published a careful new analysis in the journal Nature Astronomy, combining the latest and most precise measurements from the Gaia and Hubble space telescopes. They did something the older predictions had not fully done. They accounted for the gravitational influence of the other significant members of our local family of galaxies, especially the Large Magellanic Cloud, a substantial satellite of the Milky Way, and Andromeda's own large companion, the Triangulum Galaxy. When they ran the numbers not once but through 100,000 simulations, sampling across all the uncertainties in the positions, motions, and masses of these galaxies, the supposedly certain collision dissolved into a coin flip. Their conclusion was that there is only about a 50% chance the Milky Way and Andromeda actually merge within the next 10 billion years. Half the time, in their simulations, the two galaxies simply passed each other by sweeping close, perhaps within a few 100,000 light-years, but not colliding, drifting apart again to continue their separate lives, at least for a long while. Why did the certainty collapse? For exactly the reason this whole story keeps circling back to too many variables, each carrying its own measurement error, compounding into a wide spread of possible outcomes. The Large Magellanic Cloud, it turns out, tugs the Milky Way off to one side, nudging it out of the plane of a head-on approach and making a clean collision less likely. Triangulum pulls the other way, making a collision somewhat more likely. Depending on the precise masses and motions which we do not know perfectly, the system can tip either way. It is the same lesson as the encounter list we built earlier, written now at the scale of entire galaxies. Our predictions are only as certain as the map, and the map has error bars, and over long enough spans those error bars swallow the answer whole. This matters enormously for Voyager 2, because it means we cannot even specify the stage on which the spacecraft's deep future plays out. Consider the branching possibilities. In one scenario, the Milky Way and Andromeda do merge. The two spirals tear through each other over hundreds of millions of years, their gas clouds colliding and igniting bursts of new stars, their neat spiral structures scrambling and eventually settling into a single vast, smooth, elliptical galaxy. In that case, Voyager 2, assuming it is still bound, would find itself orbiting within a completely transformed galaxy, one with a different shape, a different mass distribution, a different gravitational character than the Milky Way it started in. Its orbit would have been violently reshuffled during the merger, as the whole gravitational landscape it was riding got torn up and rebuilt. Older modelling of that merger scenario gives a concrete sense of just how violent the reshuffling could be. Researchers at the Center for Astrophysics, run jointly by Harvard and the Smithsonian, examined what a Milky Way and Andromeda merger might do to a system like our own Sun's, and found that the collision could fling such a system roughly 3 times farther from the galactic centre than it sits today, hurling it out into the sparse galactic suburbs as the two galaxies' gravity tore up the old orderly orbits. They also found something starker, a small but real chance. They estimated around 1 in 8 that a system could be ejected from the merged galaxy entirely during the upheaval, thrown clear into intergalactic space in the chaos of the collision. Now apply that to Voyager 2. If a merger does occur, and the spacecraft is still bound at the time, Then, whatever orbit it had been patiently tracing gets torn up in exactly this way, either flung outward onto a vastly larger loop through a transformed galaxy, or, with a smaller but genuine probability, cast out of the galaxy altogether. A single event, lasting a few 100 million years, could undo billions of years of accumulated orbit and reset the spacecraft's entire future in one stroke. This is why we cannot even name the container. In another scenario, the galaxies merely pass each other, a near miss that distorts both spirals with tides flinging out long streams of stars, warping their disks without fully combining them, at least not for a long time. In that case, Voyager 2 rides through a galaxy that has been disturbed and stretched but not destroyed. And in yet another, the interaction is gentler still, or delayed far longer than expected. Each of these produces a different environment, a different gravitational field, a different set of possible orbits for the spacecraft, and we cannot say which one will happen. The most honest statement is that the future of the Milky Way itself is now an open question, and if we cannot pin down the galaxy, we certainly cannot pin down one small machine adrift inside it. There is a subtlety worth adding to the near-miss branch, because it is easy to hear 50% chance of no collision, and picture the two galaxies sailing past each other and parting ways forever. That is not quite what the near-miss scenario means. Even the simulations in which the Milky Way and Andromeda avoid a direct collision in the next 10 billion years often do not have them escaping one another for good. When two galaxies of this size sweep past each other, they plough through each other's outer halos of stars and dark matter, and that passage acts like a brake. The drag has a name: dynamical friction, and it works by bleeding orbital energy out of the two galaxies as they pass, so that each swing carries them a little less far apart than the last. In many of these scenarios, the galaxies fall back toward each other and, after one or more of these decaying passes, merge anyway just later, and after a more prolonged and complicated dance. For Voyager 2, this means the branching future is even richer than a simple fork between merges and never merges. There is merge soon, in a few billion years. There is pass then merge, drawn out over a much longer span, with the spacecraft riding a galaxy that is repeatedly disturbed, stretched, and reshaped by successive close passes before the two finally combine. And there is the genuine possibility of no merger at all within the timescales that matter here, the two giants settling into a long mutual orbit. Each of these writes a different history for the galaxy that carries the spacecraft, and therefore a different, unknowable history for the spacecraft itself. What we can say is that across 10 trillion years, the odds that Andromeda leaves the Milky Way permanently and completely untouched are slim. One way or another, on one schedule or another, the neighbourhood the spacecraft rides through is going to be rearranged. Notice what has happened to the layers of uncertainty over the course of this journey. At the outset, a single well-understood gravitational field. The suns let us predict the spacecraft's path almost perfectly. Then the multiplication of poorly mapped stars degraded that prediction into a provisional, ever-revised forecast. Now, two new sources of uncertainty have piled on top. First, gravitational scattering by countless stars randomizes the spacecraft's orbit over billions of years, turning its trajectory into something fundamentally unpredictable, rather than merely hard to compute. And second, the galaxy itself, the very container the spacecraft orbits within, has become a variable, its own future hanging on a coin flip between merger and near miss. Each larger timescale has stripped away another layer of certainty. We began with a measured line. We now have a probability cloud inside a galaxy whose shape we cannot forecast, and we have not even reached the timescale the story is named for. And yet this is important: we have not fallen into pure ignorance. This is the discipline the whole subject demands, distinguishing what we cannot predict from what we still can. We cannot predict Voyager 2's specific orbit in the deep future, or which stars it will pass, or whether its galaxy merges or misses, but we can still say meaningful things about the range of what is possible, because the underlying physics still holds, even when the specific outcomes do not. We know the spacecraft is bound to the galaxy, because its speed is far below escape velocity. We know it will orbit the galactic center on a timescale of a couple 100 million years, because that is how gravity works at that distance. We know gravitational scattering will slowly reshape that orbit, because that is the inevitable statistical consequence of countless stellar passages. We know physical collision with a star will remain extraordinarily unlikely across the entire span, because the galaxy is overwhelmingly empty. And we know the galactic environment will change dramatically, even if we cannot say exactly how, because Andromeda is coming one way or another. These are not predictions of a specific fate. They are the firm boundaries within which every possible fate must lie. The map has lost its detail, but it still has its edges. That is the honest shape of Voyager 2's future as it enters the truly deep timescales. Not a route, but a widening fan of possibilities, bounded by physics we understand, spread wide by processes we cannot follow in detail. The spacecraft is a bound object on a galactic orbit, being slowly scattered onto ever less predictable paths inside a galaxy that is itself heading into an uncertain transformation. Every one of those statements is defensible. None of them can be sharpened into a coordinate, and we are still not there. We have followed Voyager 2 from the last human signal, through the Oort Cloud, past its named stellar encounters, into its long galactic orbit, and up to the great uncertain interaction with Andromeda, an event that plays out over the next several billion years. But billions of years are not trillions. The question that named this entire journey reaches 1,000 times further still, out to 10 trillion years, into an era so distant that even the merger with Andromeda, whether it happens or not, will be ancient history, a thing that occurred in the first tiny fraction of the spacecraft's long existence. Out there, the sun will be long dead. The familiar stars will be gone. The galaxy, merged or not, will have aged into something we would scarcely recognize. And still, if it has survived, some remnant of a machine built by human hands in the 1970s will be turning, silently. On the 30,000th or 40,000th loop of a wheel, no one is left to measure. It is time, at last, to reach the full span of the question to stand 10 trillion years from now, and ask what, if anything, can honestly be said about where Voyager 2 will be. Let us finally go there. Not 1,000 years, not 1,000,000, not even the few billion it takes for Andromeda to arrive or not arrive. Let us stand 10 trillion years from now and look for the spacecraft. To even approach that number honestly, you have to first feel how far out it sits. The universe right now is about 13.8 billion years old. 10 trillion years is over 720 times that entire history. Everything from the first light after the Big Bang to this very sentence, replayed 700 times over, and only then do we arrive at the moment we are asking about. Every span we have crossed so far in this story, the dying of the spacecraft's power, its passage through the Oort Cloud, its encounters with Ross 248 and Sirius, its long scattering through the galaxy, the whole drama of whether the Milky Way merges with Andromeda, all of that unfolds within the first tiny sliver of these 10 trillion years. The Andromeda question, which consumed us a moment ago and which reaches several billion years into the future, is settled within the first 1,000th of the timescale we have now reached. We have spent this entire journey climbing, and only now have we arrived at the mountain the title pointed to all along. And the first thing to say about 10 trillion years is something that runs against every cliché about the far future. It is not the end of everything. This is where a lot of documentaries reach for darkness and cold and a dead, black universe, and it would be dramatic, but it would not be true, and the truth is stranger. 10 trillion years from now, stars will still be shining. Not stars like our sun. Those live only about 10 billion years, and every sun-like star will have long since burned out and collapsed into a slowly cooling ember. But the galaxy is full of smaller, dimmer, vastly more patient stars, the red dwarfs, which make up the great majority of all stars that exist. A red dwarf sips its fuel so slowly that it can go on burning for trillions of years, some of them for 10 trillion years and beyond. Astronomers who have mapped the deep future of the cosmos place the true end of the age of starlight, the era when stars are still being born and still shining, at around 100 trillion years. 10 trillion years is only a tenth of the way to that ending. So the sky Voyager 2 drifts through at our chosen moment is not empty and dark. It is dim, reddened, thinned outer galaxy lit by the long, cool glow of red dwarfs, with the bright, hot stars all gone. It is twilight, not night. The spacecraft, if it survives, coasts through a galaxy grown old but not yet dead. So, set the stage that way. A faded, red-lit galaxy, 10 trillion years hence, most of its brilliant stars extinguished, its patient dwarfs still burning low, and somewhere within it, or perhaps no longer within it, is the object we have been following. Where exactly is it? Here we must be more disciplined than at any other point in the story, because the honest answer is not a place. It is a distribution of possibilities, and the intellectual courage of this whole exercise lies in refusing to collapse that distribution into a false certainty just because a single answer would feel more satisfying. We cannot give a coordinate. We cannot name a star. What we can do, and this is not nothing, is lay out the range of states the spacecraft might be in, ordered by how defensible each one is, bounded by physics we genuinely understand. Begin with the most likely state, the one the physics most strongly supports. 10 trillion years from now, Voyager 2 is probably still gravitationally bound to the remnant of its home galaxy, whether that is a still recognizable descendant of the Milky Way or the merged, settled elliptical galaxy that would result if Andromeda did collide with it long ago. The reason this is the leading scenario comes straight from the timescales we established earlier. The process that eventually tears galaxies apart, the slow evaporation of a galaxy as gravitational scattering flings its members outward, one by one, operates on a timescale of around 10 to the 20th power years. That is 100 quintillion years, roughly 10 million times longer than the 10 trillion years we are considering. At 10 trillion years, galactic evaporation has barely begun. Most objects that started bound to the galaxy are, at this point, still bound. So the single most probable statement we can make is this: the spacecraft is most likely still inside a galaxy, still orbiting its distant center, still riding the great wheel we described before. But being still bound does not mean being where it started, and this is where the scattering we traced earlier has done its slow, thorough work. Across 10 trillion years, Voyager 2, if it remains bound, will have completed something on the order of 40,000 orbits around the galactic center, each orbit a couple hundred million years long, each one subtly nudged by the countless distant stars it drifted past. The cumulative effect of 40,000 orbits worth of gravitational scattering is not a small correction. It is a total scrambling of the spacecraft's original path. Whatever tidy orbit it inherited when it first fell into the galaxy's grip has, by now, been kicked and reshaped so many times that no trace of the starting conditions survives in it. The spacecraft might be looping through the crowded inner regions of the galaxy on some passes and out into the sparse halo on others. It might be on an orbit tilted far out of the galaxy's plane or plunging steeply through its center. The point is not that we can name which of these it is. The point is that the connection between where it began and where it ends has been severed by the sheer accumulation of random nudges. Its location is not merely unknown to us for lack of data. It is fundamentally unknowable because the process that placed it there erased its own history as it went. That is a crucial distinction, and it deserves to be stated plainly because it is the deepest reason the title's question has no coordinate for an answer. There are two kinds of "we don't know." One kind is practical. We lack the measurement, but a sharper instrument could supply it. That was the earlier kind of uncertainty, where a better star catalogue could refine the encounter list. The other kind is fundamental. No possible measurement taken today could ever specify the answer, because the outcome depends on a chain of essentially random events that has not happened yet and cannot be run in advance. Voyager 2's position at 10 trillion years is the second kind. It is not hidden from us. It is undecided, being written, slowly, by 40,000 orbits of chance that no calculation performed now can outrun. This is why every honest scientist stops short of naming a place. The place does not exist yet, and never will exist in any form we could have predicted. Now widen the fan of possibilities, because most likely still bound is not certainly still bound. There is a real, if smaller, chance that across 10 trillion years the accumulated scattering, or one unusually forceful stellar passage, or the violent gravitational upheaval of a galactic merger gave the spacecraft enough of a kick to unbind it entirely. In that scenario, Voyager 2 is no longer inside any galaxy at all. It has been flung out into the immense emptiness between galaxies, drifting through intergalactic space far from the red-lit disk it came from, coasting through a darkness deeper and more absolute than anything within a galaxy. Galactic evaporation may not fully strip a galaxy for 100 quintillion years, but it does not act all at once at the end. It is a steady leak, and the rate is the key. Across a mere 10 trillion years, only a small share of a galaxy's members have leaked away, which is precisely why ejection is the minority outcome rather than the expected one. Still, a small share is not zero, and the spacecraft could fall within it, a scientifically legitimate possibility that honesty requires holding open alongside the others. So even at the coarsest level, the level of is it in a galaxy or not, we cannot give a single answer. We can only say, probably yes, possibly no, and no measurement we could make today would settle which. And there is one thing across this whole widening fan of possibilities that we can say with real confidence, precisely because it is a statement about physics rather than about a specific path. Across all of these 10 trillion years, through all the scattering and all the orbits and all the possible ejections, the spacecraft has almost certainly never struck anything. Recall that the timescale for Voyager 2 to physically collide with a star was estimated at around 10 to the 20th power years, the same 100 quintillion year scale as galactic evaporation, 10 million times longer than our question. The galaxy is so overwhelmingly empty that even across 10 trillion years of wandering, the chance of the spacecraft actually hitting a star, or a planet, or almost anything at all, remains vanishingly small. This is the strange gift of cosmic emptiness. It makes the spacecraft's trajectory impossible to predict, yet it also makes the spacecraft's survival, against collision at least, almost assured. It will be scattered 1,000 times. It will be struck essentially never. Whatever else is true at 10 trillion years, the object has almost certainly not been destroyed by impact. But now we arrive at the subtlest and most important question of all, and it is not really a question about location at all. We have been asking where the spacecraft will be. The deeper question is what it will be, because there is a world of difference between an object continuing to exist, an object remaining intact, and an object remaining recognizable, and across 10 trillion years, those three fates come apart from one another completely. Consider what 10 trillion years does to a physical object, even one that never hits anything. The spacecraft is not truly safe just because it avoids collisions, because it does not travel through perfect nothingness. Interstellar and intergalactic space, however empty, still contain a faint sleet of high-energy particles, cosmic rays that stream through everything endlessly and slowly damage the materials they pass through. Over eons, cosmic rays gradually alter the atomic structure of solids, embrittling them, degrading them at the molecular level. There is also dust, not enough to stop the spacecraft, but enough that over 10 trillion years the object will drift through vast, tenuous clouds of it, and every grain that strikes at orbital speed sandblasts its surface by an infinitesimal amount. The researchers who modelled the far future of the Voyagers and their golden records specifically traced the spacecraft through the dust clouds they would encounter, estimating how those passages would slowly erode the craft over immense spans of time. None of this is fast. A single cosmic ray, a single grain of dust, changes almost nothing. But 10 trillion years is the ultimate patient sculptor. It has time enough for the slow processes to finish what the fast ones never could. So walk the three fates apart. Will the spacecraft still exist at 10 trillion years? Will its matter still be there? Almost certainly yes. Atoms are hard to destroy, and the spacecraft is made of durable metals, aluminum, titanium, gold-plated copper. The stuff of it will persist. Will it remain intact? Will it still hold together as a structured object, rather than a scatter of pieces? That is far less certain. 10 trillion years of cosmic ray embrittlement and micrometeoroid erosion and thermal cycling could well loosen joints, fracture booms, and shed components, so that what began as a single assembled machine slowly becomes a loose association of fragments drifting along the same path. And will it remain recognizable? Would anything, coming upon it, be able to tell that this was a spacecraft built by hands, launched from a planet. That is the least certain of all. The fine details that make it legible as a made thing, the shape of the antenna dish, the arrangement of instruments, the etched markings, are exactly the delicate features that erosion attacks first. A structure can survive as bulk metal long after it has stopped looking like anything in particular. The mountain endures. The sculptor's fine lines wear away. Nowhere does this matter more than for the golden record, the gold-plated copper disc bolted to each Voyager, carrying sounds and images of Earth, a greeting cast into the dark on the faint hope that something, someday, might find it and understand. The record was designed with the deep future explicitly in mind. Its makers chose materials meant to last, and the research modelling its fate suggests that as a physical disc it could survive, in some form, for an extraordinarily long time, potentially billions of years, one of the longest-lived artifacts humanity has ever made. But surviving as a disc and remaining readable are two different things, and this is the fifth and final fate we must separate out. The information on the record lives in the microscopic grooves and markings pressed into its surface, precisely the scale of detail that cosmic rays and dust erosion degrade over time. Long before the disk itself crumbles, the fine encoding that makes it a message rather than a blank metal circle would likely be worn away. So we must be careful and honest here, and resist the sentimental ending. We cannot promise that the golden record will still be playable at 10 trillion years. What we can say is that some remnant of the disk may well still exist as an object. While the human voices and images it carries have most likely long since faded into unreadable erosion, the bottle may outlast the letter inside it. And here we must be equally honest about the record's original purpose. It was sent as a message to whoever might find it. But across 10 trillion years, in a galaxy of red dwarf twilight, adrift on an unknowable orbit or thrown clear into the void between galaxies, the odds that any finder ever comes upon it are so remote that we cannot responsibly build the story's ending on that hope. The record was never really a reliable letter to the future. It was something else, something more honest and more human, and we will come to what it truly was. Step back now and take in the full, honest answer to the question that named this journey. Where will Voyager 2 be in 10 trillion years? The most defensible response, assembled from everything we have followed, is this. It will most likely still exist as physical matter. It will most likely still be bound to the aged remnant of a galaxy the Milky Way's descendant, or a merged galaxy grown from it, though there is a real chance it has been flung into intergalactic space. It will almost certainly not have collided with anything. Its orbit will have been scrambled by tens of thousands of loops around a galactic center into a path with no traceable connection to where it began. It may still hold together as a recognizable structure, or it may have eroded into a loose drift of fragments. And whatever remains of the golden record is most likely a worn disk of metal whose message has long since been sanded away by cosmic rays and dust. That is the answer. Not a coordinate, not a star. A range of states, each bounded by physics, none sharpenable into a point because the universe genuinely has not decided yet, and the deciding is done by processes that erase their own tracks. Some will find that answer frustrating. I think it is the most interesting answer there could be. And here, only here, at the very end is where we are allowed to say why it moves us. For the whole of this story we have watched certainty drain away layer by layer. We began with a spacecraft we could track to the kilometer, whose speed and heading we had measured with our own instruments. We ended with an object whose very galaxy we cannot name. Every step outward in time stripped away another kind of knowing. First the ability to command it, then the ability to hear it, then the ability to compute its encounters, then the ability to predict its orbit, then the ability even to say which galaxy would hold it. And that draining is not a failure of science. It is science being honest about the shape of reality. The universe does not owe us a knowable future, and the deep future of one small object, tossed on the accumulated chance of 10 trillion years, is simply not a thing that can be known. There is a strange dignity in a discipline willing to follow its own reasoning all the way to we cannot say, and to stop there rather than invent a comforting coordinate. But notice what does not drain away. Through every layer of lost certainty, one thing remains absolutely fixed, and it is the thing we knew first. The spacecraft keeps moving. Silence did not stop it. The death of its power did not stop it. The loss of every human who ever knew its name will not stop it. It coasts on the momentum given to it by planets during a few brief encounters in the 1980s, and that momentum is now effectively permanent, carrying it forward long after everything that launched it has vanished. There is something almost unbearable in that image, a made thing, mindless and unaware, faithfully continuing a motion begun by a civilization. It can neither remember nor represent. It does not know it is carrying our greeting. It does not know the sun has died. It does not know we are gone. It simply goes, because nothing tells it to stop. And this is where Voyager 2 splits into two separate legacies, and where the real meaning of the journey finally shows itself. There is the physical object, the drifting matter, continuing without intention, without awareness, without any purpose it could possibly hold, an ancient shard of metal following a law of motion through a red-lit galaxy or the dark between galaxies. That object's journey is not a story of arrival. It never reaches a destination. There is no star it is bound for, no finder it is fated to meet, no coordinate where the trip concludes. It just continues and continues until on timescales far beyond even 10 trillion years, the slow processes finally win. That is the first legacy. Pure, blind, physical persistence. But there is a second legacy, and it is the one that actually matters, because it is the only one that ever had meaning in it. It is not the object, it is the decision to send the object at all. 10 trillion years from now, no human will remember that a species on a small planet, having existed for only an eye blink, and knowing full well the odds against anyone ever finding their message, chose to build something durable and fling it outward anyway, not because it was useful, not because it would come back, but as an act of reaching, a refusal to be entirely silent. That choice is not carried in the grooves of the record, which will have eroded. It is not carried in the structure of the craft, which will have decayed. It is carried nowhere at all in the far future. It survives only in the fact that it once happened. The spacecraft is the artifact of a gesture, and the gesture was always the point. We did not send Voyager 2 because we expected an answer. We sent it because sending it was a way of saying that we had been here, and that we wanted to be part of something larger than the little span we were given. So do not picture, at the end of this, a triumphant arrival. Do not picture the record being lifted by curious hands on some distant world. That is a hope we have no honest right to promise. Picture instead the truer thing. Picture a worn piece of matter, its markings long since sanded smooth, drifting on an orbit no one plotted, through a galaxy dim to embers, 10 trillion years after the hands that made it turn to dust, and the sun that warmed those hands went cold. It is not lost, exactly, because to be lost you must have had a place you were supposed to be and it never did. It is simply still moving, an object that has outlived its makers, outlived its message, outlived its star, and outlived every map that humanity could ever have drawn for it. We built something that escaped not just the sun's gravity but the reach of our own knowing, and that is not a defeat. It is the most far-reaching thing we have ever done. The spacecraft will go where we cannot follow and cannot see, and the going itself begun by us, continuing without us, is the whole of what we meant to say.